Hey, so welcome today. Part of my change in appearance, we're in a planning day today. Again, the lesson that we're going to be covering was our Friday, October 10th lesson. We're doing pre-planning. Forgot that I was going to be filming a video, so I didn't bring a button up, didn't do my hair. So it's going to be slightly different. Hope that doesn't take away from the lesson because we're going to go through just like we did in class. So today we're going to be graphing linear equations in standard form. Now, one of the things with standard form that we want to go over is that there is no correct nor incorrect form of a line. There are useful forms that we like to go over. One of them is standard form, which means everything's been simplified. Everything is a full integer value and there's no negatives. Or what a lot of people say is there might be negatives, but there's no subtraction. We're going to go over kind of a caveat about that. Over the next few lessons, we're going to cover standard form, slope-intercept, and point-slope. All of them are correct forms of a line. Technically, any equation that you have that has two variables are forms of a line, and if they're a useful form, use them. This is one that we consider useful in a strictly academic context because, again, everything has been simplified. But forms of a line, I think it's often misconstrued that this is correct, this is incorrect. It's kind of like language. If I say, hey, I would like to go to the store, or if I say, hey, I'm going to go to the store, or if it's like, hey, I go store. The message being conveyed is correct. Whatever's more useful to you, you keep with it. We're going to jump off into standard form. So standard form is ax plus by equals c when a, b, and c are all non-negative integer values. This non-negative you'll see will pop up a lot in some of our equation forms. And that stems over from a very, very old tradition. If you look back way in the history of how equations were set, a lot of mathematicians didn't like negative numbers because there was a strong, and I'm not really kidding about this, unnatural, some even would say like evil representation of negative numbers, because in the early history of mathematics, we're talking like medieval times here, so not too terribly early. Negative numbers didn't make sense to the common public. They're like, how do I have negative apples? If I eat negative bowls of cereal in the morning, what are you talking about? And because they couldn't see the real world context, they deemed this as otherworldly, unnatural, and therefore evil. So a lot of mathematicians did a lot of things to move negatives around, to hide them, so that if we had a negative pop up here, well, let me just move it to the other side of the equation. Now there's no negative anymore. Now that's considered a good equation. There's nothing wrong with negatives in standard form, and you're kind of seeing that go away. But for the most part, if you see a lot of non-negative requirements, it usually stems from that. Early people didn't understand, or the early general population didn't understand the concept of negative values. Now we do. You see a negative account balance, it's not like, oh my God, I'm worshiping the devil. It's like, I just have bad financial planning. So again, it's going to take a long time for this to completely disappear, but that's just a little tidbit off to the side. One of the things that I like to point out as far as we're trying to be able to look at equations here and kind of know what the graph is going to be looking like. The graphing part here, the students should be familiar with, however, most of them aren't because they've forgotten it. We want to be able to get to the point by the end of this chapter being able to look at an equation and kind of mentally know, I know this graph is going to be steep, I know this graph is going to be relatively flat, I know this one's going to be really steep, I know it's either going to be shaped like this or it's going to be shaped like that, whether we're looking at negative or positive slopes, and just general ideas. So I say the larger the value of the coefficient, the larger it has an impact on the graph. I said it looks more like that axis. It should be more looks like the other axis, but we'll see what happens here in a moment. So the first thing that we're going to look at is when A or B has no impact, when we're going to zero them out. The graph is either going to be a horizontal or vertical, because we've completely removed the impact of one of the two variables. So we might get equations that look like this. Now, realistically, we're not going to have the equations set up to look like that. They're going to eventually turn into that. Or set up to look like that. We're going to turn them into something more useful. So if I don't have an x term, that's 0x, the x has been completely removed from having an effect on the equation. So what's left over is I have 2y equals 8. At this point, I'm going to try and solve, when I only have one variable, I'm going to try and isolate the one variable. So I'm going to get rid of the 2 by dividing both sides by 2, and I get y equals 4. That is the equation that I'm going to be working with here. So we're going to do a generic 5 by 5 graph, which means 5 up, 5 down, 5 left, and 5 right. You're going to need 10 spaces overall to see what this graph looks like. Now, I've noticed a lot of the students, I don't think are quite ready for graphs at scale yet. Again, this should be something that they already know, but I'm noticing that a lot of the students are really struggling. So I'm not sure if maybe they just weren't covered well in either middle school or the years prior, or maybe they just have genuinely forgotten, or if they're just trying to, pull the old student, I don't remember how to do that, so therefore I don't need to do it now. But we're going to stick with some generic graphs for the next few sections until we get back into the groove of scaling these and moving the centerpiece around to where it's needed. First thing I asked them is, do we remember where the x and the y-axis are? Most of them do. They remember that this is the x-axis, the left and right axis. The up-down axis is my y-axis. There we go. It's an ugly y, but it'll do. And then I ask, okay, where does the y value equal 4? Almost 100% of the time they know where y equals 4, and it's right there. Now, the next part is where I get a lot of divergence. When I say, okay, well, where else does y equal 4? Because it can be 4 in more than one spot. 5 out of 6 classes all basically said the same thing. -4. My response is -4 positive 4? No. So they're like, okay, well, don't go down. I'm like, well, where else could we be? Well, how about x equals 4? No, that's I need y equals 4. I don't need that spot right there. -4 on the x. Well, that's also, not only is that negative, but that's also not y again. So 5 out of 6 classes pointed to the other values of 4 away from the origin. So I think they're remembering the absolute value idea, but I don't see an absolute value in this equation. I just have y equals 4. And I did have one class where somebody get it. They're like, well, how about right here? They're like, how about x equals 1, y equals 4? And I'm like, yes. If not, the analogy I usually tell them is I say, okay, let's say I'm like 5'9". So this spot right here. I'm like, where else am I 5'9"? You said to the right. So what I do is I lay down on the floor and I say, hey, am I 5'9" anymore? No, I'm actually only like 6 inches off the ground. They're like, oh, okay. I'm like, well, you said to the left as well. How about I do that? And I lay on the other side. And I'm like, am I still 5 feet 9 inches off the ground? They're like, no. I'm like, okay, so going to the left and the right doesn't count. And they're like, well, what about down? I'm like, well, does anybody have a shovel? In which case, I'm definitely not 5'9" off the ground now. And then I'm like, okay, how about I take this? Am I 5'9"? Am I still 5'9"? And then you start seeing the light bulb go off, because I'm like, hey, if you're thinking of this as, let's say, a 4 foot tall person, and you have a person that's standing and they're 4 feet off the ground, that person can move to the left and to the right. If this person moves over, are they still 4 feet off the ground? Yes. And does that stop them from moving farther over? What if I drew a person right here? Is that person still 4 feet tall? Yes. So I put a spot right there. I'm like, are they limited to going to the right? No, they can go to the left. So I can have a person that's right here, or I can even have a person that's like anywhere in between there. So this person can move in whichever direction as long as it's 4 feet off the ground. So we describe that as simply a height of 4, or I say simply an up 4. Does it have any description of the left or the right? No, because we've removed left or right from being important. As long as you are up 4, you can move as far to the left or right as possible, because there's no restrictions on left-right movement. You're always going to be 4 feet tall, no matter where you move to the left and to the right. The second thing I ask them, after they now understand this concept of removing the impact of a variable, is I say, hey, now that we know that I can put my points, anywhere along this line, is this person still 4 feet tall? Yes, 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 yes. And I start dotting all these points, and I'm like, how many dots am I going to have to make to fill in this thing? And they're like, infinitely many. I'm like, okay, what does this start to look like? It starts to look like a line, doesn't it? I'm like, yes, because y equals 4 is going to be a horizontal line at the height of 4. But now I took a shortcut and I just drew the line. How many dots would I have to put? Infinitely many. That's going to be one of the first sections in their geometry course next year, is how many points make up a line? Infinitely many. If I were to draw all those dots in order to make it look like a line, I'm going to have to draw an infinitely large amount of dots. But there we go. So I have this. This is my y equals 4. And as always, we label one specific point on the graph. That green marker is dead. So I'm going to label this one spot on the graph right there. And that is my 0, 4. That's my y-intercept. So we see the fact that when I remove the x impact on the graph, it becomes a horizontal line. So the next thing I had them write was when x disappears, it becomes a horizontal line. Okay. Then I'll ask, hey, let's look at number 2. I have a negative 3x plus 0y equals 6. The y has completely disappeared. What do we think is going to happen? It's a vertical line. They all get it at this point. So let's go ahead and let's start graphing this. If this is going to be a vertical line, let's make sure that we know what the equation is going to be. That 0y is just removed. I can ignore it because it's a 0. So negative 3x equals 6. How do I get rid of the negative 3? We're getting pretty good at everybody is saying, hey, divide by negative 3. Which is awesome because one of the hardest things to do is get them to realize that I don't add 3 there. So I have an x equals negative 2. I'm like, okay, well, I need a graph, so I'm going to do a generic 5 by 5 graph again, which means 5 spaces on every side, left, right, up, and down. Now, actually, before I do this one, another point that I made, because some of the students already get this, some of the students are still struggling with it, is when we draw our axes, you want to draw these as straight as possible. Some of them on their graph paper, they're drawing their axes like this. And I'm like, okay, we can put a little bit more effort into that. But I'm like, okay, if our y was 4, like on this one I tried to graph it, count up from 4 right here, and count up from 4 right here. Are they at the same height? And the answer is no, they're not. So be very careful with how you're drawing your axes, because if you're not putting forth enough effort on drawing this part of your graph, the rest of the graph is going to look really bad and might not make sense because it's based off a reference system that you didn't really spend too much time on. It's kind of like saying, hey, I didn't actually bother to learn Spanish, but I went off into a Spanish country and then tried to fix it. You didn't have anything in the beginning to use, so it's not going to matter what improvements you make or how careful you try and study. If you don't know Spanish, it's going to be really difficult once you get into that Spanish-speaking country. So I've got my x and my y-axis. There's my x. There's my y. And so I say, okay, where does x equal negative 2? And they get it right here. Now, my morning classes, I think it was because it was a little slow. Didn't quite get this point, but most of my afternoon classes did. So I'm assuming that when they wake up, they get the point. So looking at this, I say, where else does x equal negative 2? They're like, well, you can move down from there. And that's perfect because all of these values over there are what we call a left 2. So the way I would describe this as move left 2. And the only struggle I had was left 2 from what? Well, from the origin. In this case, it's from the y-axis. Left 2 from that spot anywhere down there. So as long as I'm moving to the left by 2 units, I can move up, I can move down, all of those as long as it's 2 units over. And then again, I follow up that with asking, okay, how many places can it actually be left to? How many little dots am I going to have to make? And they're like, infinitely many. I'm like, okay, what does infinitely many dots make? And they're like, a line. Perfect. I have my line right there, right there. I label my one intercept, which this case is negative 2, 0. And I say, okay, describe what happens when I remove the y from having an effect on the equation. Well, when height has no bearing on the equation, I can only be concerned with the left or right motion. So therefore, when y disappears, it becomes a vertical line. Awesome. So now we're going to move into some other equations where maybe it doesn't completely disappear, but partially disappears. which means I'm going to have something in between a horizontal and a vertical line. And so what is between a horizontal and a vertical line? A diagonal line. So we're looking at the degrees of diagonality of these lines. If something has a larger effect of x, it might be more closely related to vertical, so it's going to be close to vertical. If something has a larger y, it might be closer to horizontal. If they're roughly even, it might be evenly well balanced. So let's go ahead and take a peek at that. Okay, so I've set up a Desmos presentation here to kind of explain to them what happens when we have our horizontal and our vertical lines merge between the two. So ignore these two parts of the thing. I just made the axes a little bit bigger. On the actual graph, you couldn't really see them too terribly well, so I said, hey, let's thicken up these lines. What we're looking at is this equation right here, which as of right now is my diagonal line. And I say, okay, we were concerned with ax plus by equals c. What happens when I modify the a and the b in relation to each other? Because right now I have an a, I have a 1x plus a 1y equals 1. So what happens when I modify the two variables? So what we do is we take the a value and I say, hey, what happens if I increase the x aspect of the graph in relation to y? And they go back to what happens if the x was removed. They're like, okay, well, when x was removed, that became a horizontal line. So what happens if x is added in? Well, that should turn it more vertical. So if I increase the a value, let's see if it becomes more of a vertical line. And yes, it does. As I increase that value, it becomes more vertical. And as I decrease the value of a, it becomes more horizontal. And they're like, well, can we decrease it even more? Can we decrease it down to 0? Sure. Let me actually modify this between 0 and 10. Do the same with b. 0 and 10. Okay, so the a value, I can go all the way up to 10, or I can go all the way down to 0. And if I make it all the way down to 0, I do end up getting a horizontal line. But if it's anything other than 0, like 0.1, we see the fact that line becomes slightly diagonal. And if a and b are the same value, I get a perfectly diagonal line. Okay. What happens if I increase b, which is the number in front of y? I increase its impact, its influence on the graph. Well, let's take a look. We know that when I completely removed y, I got a vertical line. Or sorry, when I completely removed y, I got a vertical line. So if I add its impact, I should be going more horizontal. So as I increase b, yep, it gets more and more horizontal. And you can see that as I got up to 10, it's really, really, really flat because the y is 10 times more important than the x. I can increase this further and further and further, like let's say between 0 and 100. Let's see. So I can make it flatter and flatter and flatter to the point where it almost looks flat. And if you could see, you probably can't on camera right now, there's a little smidge of the axis under and a little tiny smidge, like I can barely see it over here, a little smidge of the axis above, which means this isn't quite perfectly flat. But the bigger I make the y impact in relation to x, the flatter it gets, the more horizontal it becomes. Let's go back and let's put this to a value of 10. Boom, there we go, and I'll put these both at 1. Some students will ask, well, what happens if we increase them both in relation to each other? Remember, this is which has a greater impact. So if I increase 1, that'll change the orientation of the line, but if I increase both of them, the line's orientation isn't going to change very much. So let's crank this one up. See, right now I have a diagonal line. If I crank this one up to 10 and this one up to 10, I get my original diagonal line back. But there's a small caveat for those of you who've noticed to spot that. Let's put both these back at 1. And when I increase the value by 10, it does have a secondary effect on the c variable. For you guys right now, the next thing I ask them is, okay, what happens if I change the c? Almost all the classes, I think 5 out of 6, first period I don't think said anything, but most of them say when I change the value of c, they're like, well, the line gets shorter. I ask them, well, how far does a line go in each direction? Infinite. Okay, so if it's infinitely big, how does the line get shorter? What's half of infinity? It's infinity. What's a quarter of infinity? Infinity. So it's not going to get shorter, and they're like, well, it's going to get thicker. A line is a series of points. It's not going to get any thicker. This is thick on the board, but that's because I've artificially made it bigger so we can see it. And they usually don't come up with a very good answer because they don't really know what happens. I did have one class, I think it was like 4th or 5th period, probably 5th. Somebody said, oh, it's going to move up or down or left or right. No, 6th, because 6 actually said translation, so somebody knew what they were talking about. When I modify C, it moves the graph, and I ask them, is this moving up and down, or is it moving left and right? The answer is, with the equation of a line, I can't really tell. I don't know if it's moving up and down, or if the graph is moving from the left to the right, or if it's doing them both at the same time. But the C is going to affect what we call a transformation, specifically a translation of the graph. A translation is when I take the graph and I move it as it originally looked, no matter what shape it was. I take it and I move it either up, down, left, or right, or some combination therein. I don't take it and adjust the graph as I move. That's a different type of transformation. I literally take the shape and I move the shape somewhere else. So, awesome. Let's go ahead and do the next set of questions now that we understand what's happening there. Okay, so we've got our second set of questions. Now, this is when I have the x and the y are both impacting the graph, but to varying levels. Here, the y is 1 unit more than the x. Here, the x is 1 unit more than the y, but I start asking, what is the relative difference? This, albeit they're both 1 apart, this y is only 33% more than the x. It's 1/3 bigger because it's 4 versus 3. This one, x, is 100% bigger. It's much larger because it is twice as big as the y. Here, the y is 200% bigger. It's 3 times the size of x. So again, we're going to see varying degrees. They're going to get increasingly separate from each other. So what does that have an effect on the graph? Okay. Well, there are 3 questions to ask. One that's going to help us get an idea of what the graph's going to look like, and it's, who has the greater impact? Here, y has a greater impact. We know that when y had all the impact, it was a horizontal line. So I'm going to take my perfectly diagonal line, actually from your perspective it'll look like this, and I'm going to turn it a little bit more horizontal. So I'm just going to nudge it a little bit down. The greater y becomes in relation to x, we saw that the graph is going to flatten out more and more and more. But because this is only a little bit bigger, just a little bit flatter. So I'm going to say that this is slightly more horizontal. Okay. Does that help us actually graph it? No, but it gives us an idea of what to expect when graphing. So there are 2 things that I'm going to need to figure out. Okay. First is, what are the intercepts? Now, some of the classes, we've already done this once this year, and they've done it in years prior. A lot of them are still just forgetting what intercepts are, and we're having to go back and reteach that. So I had some of the classes write this down. When you have an intercept for any variable, plug in a 0 for the other variable. So if I'm plugging in an intercept for y, I plug in a 0 for the other one, x. If I'm finding an intercept for x, I plug in a 0 for the other one, y. No matter which variable I'm trying to find, plug in a 0 for the other one. Trying to find y, plug in a 0 for x. Trying to find x, plug in a 0 for y. That's it. Okay. And then we're going to graph it. So here we have the x-intercept, and I have the y-intercept. I'm just abbreviating x-int and y-int for intercept. Okay. Now, remember we just said, if I want to find the intercept for x, plug in a 0 for y. So I'm going to say this is 3x plus 4 times 0 for y equals 12. Do you see how I replaced y with 0 when finding the x-intercept? When I want to find the y-intercept, I plug in a 0 for the x. basically when I want to find out what point is the most effective on x, I have to remove y. When I want to find the point where it crosses y, I have to remove x. That's all we're doing here. Okay? And then the rest of this, okay, I want to be able to solve this, so I'm going to say 4 times 0 is 0. I can eliminate that. I'll get 3x equals 12. Then I say, okay, how do I get rid of the 3? Divide by 3, so x equals 4. Here is my x-intercept, is at x equals 4. For the y-intercept, 3 times 0 zeroes out. That is completely removed, so I end up with 4y equals 12. How do I get rid of the 4? Divide by it. So I get y equals 3. So there is my y-intercept. And again, some of the classes I started doing the scaled graph, but I'm noticing that they're not remembering how to do that. So I've gone back to just saying, let's just do a generic 5 by 5. If I need to modify the 5 by 5 because I've got a number bigger than 5, we'll approach that here in a later section because they're still struggling with this part. So I have my x and I have my y. Okay. Now, the best part about this is this gives me my two intercepts right off the bat. So I don't need to label them because I know if x equals 4, I'm going to put a point over here at x equals 4. If y equals 3, I'm going to put a point up here at y equals 3. Bingo. So my x and my y-intercept are graphed. And I remind them because some of them are still just slapping a line. They missed 2 points. It's curved. It's not even straight. If you draw a relatively straight line, you can do that. We're not at that point yet where we need to draw precisely straight, but we do need to draw a straight line. So if you don't have a ruler and you can't draw straight, get a ruler. I can't draw straight on these whiteboards, so I have myself a ruler. I try and let them know, like, hey, look, if you can't draw a straight line, that is okay. I can't draw a straight line. I can draw close to a straight line, but don't be afraid to use a ruler. Boom. So I've got that as my line. Shoop, shoop, draw my arrows on the end. And then I tell them the most important part is, again, remember to label your intercepts. So this is 0, 3 for my y-intercept, 0, 3 for x and y, 4, 0 for x and y on my x. So 4, 0. Bingo. And that's it. Now, we notice that after we've graphed that, let's double check. We said it's slightly more horizontal. If this was perfectly diagonal and I go from 3 to 3, I notice that it's a little bit more horizontal. Not a lot, but a little bit. So we're doing good. Let's do the same with this one. Now, if y is more important, it's more horizontal. What happens when x is more important? Well, it's going to be slightly more vertical. Not just slightly, but it's twice as important as y. So it's going to be more vertical. And then we're going to say, okay, now that I know how to do that, I need to find what are the intercepts so that I can graph it. And remember, an intercept is when I plug in a 0 for the other variable. I want to know what the effect is on x, I have removed the y. I want to know what the effect on y is, so I have removed the x. So I'm going to take my x-intercept and my y-intercept. Okay. For my x-intercept, I plug in a 0 for the y. 2x minus 0 equals 4. And for the y, I plug in a 0 for the x. Okay. Subtracting the 0, that means that 0 doesn't exist. I'm just going to treat this as a 2x equals 4. How do I get rid of the 2? Divide by 2, so x equals 2. There is my x-intercept. Now that I have my x-intercept, I'm looking at my y-intercept next, so I'm going to solve this equation. 2 times 0 is 0, so I can just ignore that. And I have negative y equals 4. Now, I take this point because I stop and I say, hey, I get a lot of you that stopped right there. You're like, okay, the y-intercept is 4. Close, but we're not quite done yet. What number is in front of y? Then the light bulbs come on. They're like, okay, cool. There's a 1 in front of the y. A negative 1. How do I get rid of a negative 1? Divide it. So perfect. So y is equal to negative 4. There is my y-intercept. It's not positive 4, it's negative 4. So what I'll do is everything's within 5, so I'm going to go ahead and just draw a generic 5 by 5 graph one more time. Bingo. Label my x and my y. And then I'm going to graph my 2 intercepts. Again, I found my most important points by finding those zeros. I have an x value of 2 and a y value of negative 4. So again, gentle reminder, if you can't draw a straight line, use a ruler. Can't draw a straight line on this, I'm using a ruler. Don't be ashamed, don't be embarrassed. Straight lines are hard to do. I'm going to take this and I'm going to say, okay, cool. Nope. Draw my line. Arrow, arrow. Label my 2 intercepts. This intercept is 2, 0 for x, y. And this point down here is 0, negative 4 for x, y. And then I did ask them, you notice how I always draw the line before I label the points? Is there anything wrong with labeling the points beforehand? No. Some of them did recognize that if I put 2, 0 before I drew the line, it might be beneath the line. It might make it a little more confusing to read, but it's okay. So the last one, every class I said, okay, pause, you guys graph it. And I noticed about half the kids graphed it with no issue. The other half of students, either they weren't getting some of this or they just didn't want to try because they knew we were going to put it up on the board. But I had a lot of students just not try and do anything. So I'm going to take a point right here and communicate to anybody watching this. I, as a teacher, need to be able to see what you do right and what you do wrong. If you sit here and you stare at it like this and say, I don't know where to begin, that's very difficult for me to help. I need to be able to see, okay, try and mimic what you know. And if I notice that you're plugging in a 0 for the wrong variable, I can help fix that. If I notice you're plugging in too many zeros, I can help fix that. If I notice that it's the simplification process, solving an equation, I can help fix that. If we sit and stare at this and say, I don't know what to do, I can't help fix that because there's so many things that you might not be able to do. My job as a teacher is to help fix and correct and course guide this, but I can't do all of the work for you. Mostly what we do is we show you examples, but I can't do the work for you. So we're getting to the point in the year where a lot of the students, the material is starting to get a little more difficult. We're not quite there just yet, but I'm trying to teach them persevere, try. To try and to fail is fine because we can fix that, but to not try at all, I can't salvage that. So help me, help you, help mom and dad help you. Try it. You know, if you do it wrong and you cut the grass the wrong way, mom or dad's going to fuss at you and say, hey, you cut the grass too low. It's going to take a while to fix it. That's okay. You solved the equation wrong. Hey, you can't do that. You got the wrong answer. That's okay. But we'll do better next time. And that's really mostly the focus. So at this point, you probably had a chance to pause the video and try it. Let's do it together. So this one, I see that y is 3 times the value of x. So it's not slightly more horizontal, it's much more horizontal. So I've got it much more horizontal. So when I graph my line, again, that doesn't necessarily help, but I know my line should look like this. It's much more horizontal. It's going to be much closer to flat, very flat. I don't exactly know how, but I'm expecting a line that's much flatter. So then I need to find both the x-intercept and the y-intercept. So x int for x-intercept, and then y int for y-intercept. That's an ugly y, but okay, you get it. Let's do the x-intercept first. I'm going to plug in a 0 for the y. So I have x plus 3 times 0 for the y equals negative 9. I know anything times 0 is just 0. It cancels it out, which leaves me immediately with my x-intercept of negative 9. Okay. When I do my y-intercept, I plug in a 0 for the x. So I'm going to say, okay, this is 0 plus 3y equals negative 9. That cancels out, so I have 3y equals negative 9. Now, a lot of students, they did the step right. They said, okay, y equals, but the negative sign disappeared for some reason. I think it was just because they didn't copy it down well. But that's in essence what happened. I got a negative 9 for x and negative 3 for y. So how do I graph this? Well, instead of doing a 5 by 5, I need at least 10 spaces on the left. The little graph I've got here only has 10 spaces. So I'm just going to move my axis all the way over to the right to give me 10 spaces on the left. Okay. The negative 3 fits within my 5 by 5, so I'm going to leave my x-axis right in the middle, because that'll still give me room to move down 3. X, y. Now let's go ahead and graph this. So for my x-intercept, negative 9 starts here. Count all the way back 9. There we go. I did have a lot of students also put that on the wrong side. Even though they got the negative 9, they still graphed a positive 9. The negative 3 on the y is right here. I also had another, probably about 10% of students. They swapped the x and the y when graphing. Just remember, x is always left and right, which is why we always label our axes to kind of help remind us, oh yeah, this is the x, this is the y. But I've got those 2 points. Again, don't be afraid of using a ruler. We want our lines to be as straight as possible. So pop that right there and right there. So I get that. Label my 2 intercepts. Already got this one. I know this is x comma y, which is negative 9 comma 0. X comma y. For the other one, x comma y is 0 comma negative 3. So 0, negative 3. Bingo. And that's it. So, like I said, I'm going to try and come up with a better solution, because doing these videos either on Saturday or Sunday means I have to drive up to the school. I live about 30 minutes away. And then do these videos and then go home, which, you know, not really my most desirable of options. Or I can do it on days like today where it's literally after the weekend's over. So we're going to try and come up with a better solution, because for those of you who want to get your homework because you didn't copy it down, this is the homework over 3.5. You're having to wait until today. So right now we're going to do this on page 135. Now the homework is numbers 1 through 21 odd. So numbers 1 through 21 odd, and it's all due on 10/14. So that's tomorrow, because I'm posting this video on Monday, but it's for the lesson on Friday. Now, one of the things I did want to point out is it's just numbers 1 through 21 odd. There are several that you need to do on graph paper. So numbers 1 and numbers 3 are on graph paper, and then there's another section, 9, 11, 13, 15, and 17 need to be on graph paper. So these are all on graph paper. Okay. As always, hope that answers everything. If you have any questions, reach out, and I'll see you guys tomorrow. Oh, one final thing. This week is the week of my wedding, so I will be here tomorrow to kind of get the students launched off for the rest of the week. But I'm not going to be here on Wednesday, Thursday, or Friday to help prepare for the wedding and dealing with everything that a wedding entitles to. So just be prepared for some online assignments. I know homecoming's this week, so there won't be a lot of work, because some of the days are just like parade days and whatnot. But just keep that in mind for when we attend class in the week. I'll see you guys later.